Soil is everywhere. No matter where you go on Earth, soil will always be somewhere beneath your feet. And that's a good thing. Without soil, plants would have no way to access nutrients, and the world would likely be a lot less green. So I think it's about time we all appreciate soil a little more. So here's all things soils. First, have you ever stopped to think about what soil actually is? Well, me neither, but here we go. At one time in Earth's history, early on, there was little to no soil on Earth. Instead, the surface was rocky and barren, and unlike rock and water, soil didn't come to Earth on an asteroid. Instead, it had to be manufactured here. As soon as our infantile Earth cooled, the process of weathering and erosion kicked into gear. Weathering is the breaking of rocks into smaller rocks, either by a physical or a chemical process, and erosion is when these smaller rocks are carried away from the bigger parent rocks, usually by wind or water. Depending on the size of the weathered rock, it can either be considered a clay, a silt, or a sand, with anything bigger being gravel. Out of these three though, clay is by far the smallest, while sand is the biggest, and silt is somewhere in between. Together, these three sizes of weathered and eroded rock make up soil. And depending on the ratio of these three different sizes of particles, the soil will have different properties. There's this nifty graph to help figure out what you have based on the soil's composition. So if a soil is 25% sand, 40% silt, and 35% clay, it's considered clay loam. If it's 10% clay, 40% sand, and 50% silt, it's silty loam. We could do this all day. And all these different combinations have differing properties. In most cases, however, loam is what you want your soil to be, as it's best for most types of plants to grow in. If a soil is more clay-like, it will retain more water, but plant roots will have difficulty growing through it. If it's more like sand, it'll be worse at holding water, but easier for roots to grow in. Again, silt is kinda just the in-between, and has characteristics of each extreme to lesser degrees. Overall, you want a good balance of each one. As these soils settle on top of bedrock, they form into layers called horizons. This process takes place over many thousands of years as rock is weathered and eroded, and moved from one place to another. And of course, things like this are never exact, as nature tends towards randomness. But for most places, 5 distinct horizons can typically be observed. The uppermost is the O horizon, O for organic, and this is where most of the dead plant matter called detritus is. Then there's the A horizon, that's where the real surface soil is. It's sometimes called the biomantle, because this is also where most soil organisms reside. The B is the subsurface, and usually is the furthest plant roots would go for soil. The C horizon is where the bedrock is slowly degrading into soil, so it's mostly large rocks and gravel with some soil in between. Then the R horizon, R for rock, it's just rock. Sometimes if there's a lot of soil leaching, an E horizon will develop. This is where sand and silt are deposited, while clay will continue further down into the B horizon, forming a thin light layer between the A and the B. And now here's where things get fun. Based on the development of these layers, plus 1 or 2 other conditions, we can start to classify soils all over the world into soil orders. There are a bunch of these, so you better strap in. So in the beginning, when there's soil with absolutely no development of horizons, it's an intosol. These are very young and actually the most common type of soil on Earth. Give the soil a little more time, however, and it will become an inceptisol, which has slightly more development of its layers with the beginnings of a B horizon. Then, based on the climate, given more time, an inceptisol can become a variety of different soils. At high latitudes in the Arctic or even mountain ranges, you'll have gelisols. These soils will have permafrost close to the surface, so the soil doesn't move around a lot, meaning its horizons remain undeveloped as well. These are found mostly within northern Russia and Canada. Moving slightly closer to the equator, we'll next find spotosols, which occur in coniferous and boreal forest biomes. These will be acidic due to pine needles falling to the ground and decomposing into acidic compounds. Because of this, they're low in fertility. These are primarily found in Scandinavia and the Canadian East Coast. Then we have alphasols, which have fair horizon development. They're rich in iron and aluminum, and are typically under broadleaf and deciduous forests, and also some humid Mediterranean climates. These are mostly in the east coast of the United States and the Russian heartland. Below alphasols, you'll have ultisols, which have a lot more iron in them, making them very red. These occur in subtropical locations, very humid places like the American Southeast and Southeast Asia. On roughly the same plane are iridosols. While ultisols occur in very humid places, iridosols are desert soils with extremely low amounts of water. Just think arid iridosols. These are not sand deserts, however. This is what an iridosol looks like, and this is shifting sand. They're different. Because there's little to no water in these environments, most of the small clay particles have been blown away by the wind, leaving mostly heavier sand, silt, and gravel. These are found in the Sahara, Arabia, Australia, northern China, and the western United States. Also roughly in this area are mollisols. These are dark soils and, in terms of agriculture, the most fertile soil order. order. These occur in grassland regions like the American Midwest, the Pampas region of South America, and the steppe region of Russia. Lastly, in terms of latitude, we have oxasols. These have low nutrient availability and aren't very fertile, but they do have the most horizon development of any soil order, although it's hard to see because there's so much iron in the soil, turning every layer this reddish-orange color. These are rainforest soils, think the Amazon and the Congo. Then we have a few more soils that don't really fit into the latitude scheme. These sort of just occur where they occur. In this vague category first, you'll have andisols, think like the volcanic Andes Mountains. This is recently volcanic soil ejected from a volcano. These are surprisingly rich in nutrients and given enough time create lush landscapes. Think about the volcanic islands of Hawaii and Japan. Then we have histosols. These are wetland soils. That means they're caked in water and usually feature peat. There's also going to be a lot of undegraded organic matter, which can form an impermeable layer if too much builds up. Due to the buildup of this organic matter, these will also be highly acidic. They're also unstable and dangerous to build structures on. Most of these can be found in Canada and river deltas. And lastly, we have vertisols. These also have a lot of clay in them, but they often dry out. When they do, the ground will crack and split and look like this. When this happens, soil on top will get blown into the crevices, inverting the soil layers and preventing real horizons from forming. The largest concentrations of them are found in India and Sudan. There are, of course, more ways to describe soil, and in fact, for every order, there's a suborder, a great group, a subgroup, a family, and a series. But holy crap, we don't have enough time for that. Here's a map of the actual distribution of these soil types across the planet. You'll see most of the new soils are close to the poles. This is because until recently, the poles were covered in glaciers from the last ice age, so they haven't had much time to develop. I'll leave a link for a bigger version of this map in the description. You'll notice that the soil distribution is kind of sporadic and patchy, and that's because latitude and humidity aren't the only things that determine where different orders of soil are found. In soil science, there's a common acronym, CLORPT, that's used to remember the factors that influence soil formation. First, there's climate, so rainfall and temperature and also humidity. The climate of an area is largely determined by its latitude, but also elevation and its surroundings. Then O means organisms, like how pine trees will change an alpha sol into a spotosol over time with their acidic needles. Also, soils need things like bacteria and fungi in order for plants to thrive. R is relief, or change in elevation. Mountains will channel water into valleys, so you may find a histosol at a low elevation, but an alpha sol or even an iridosol further uphill. P is for parent material. So if a soil's parent material is volcanic rock, you'll get an andesol. If a soil's parent material is limestone, it likely dissolved away and is therefore probably a clay and will also be rich in calcium. And lastly, T is time. Given enough time, the intasols and inceptisols will become more developed soil orders. I think that's it. I hope you enjoyed. This video came right out of a college notebook of mine, so these are all based on the USDA soil taxonomy, and other places might have different ways of categorizing soils. There's actually a ton more to learn about soils also, so if you want to see a video called Even More Things About Soils, give this video a like and subscribe. That's it for now. Thanks.